All right, so questions on the homework. Did you have one? Yeah. What's it say? Air and hits. Butter fat not found. Yeah, how did? Okay, so you loaded it like this. It's here, right? But when you hit, it starts fresh. So remember what we had to do? Yep. So. Yeah. So that's status. Yeah, so butterfat, that works. There. Get that line, copy it, and then get that before that first line. So first question about the homework was knitting. It was error message was butterfat not found. That means that you didn't have the line that imported the file, the CSV file, into your document. Because when it knits it, it needs to load it. It knits it and starts fresh. Other questions on knitting? Yep. Error? All right. It's your error. What did you? Oh, you called it. That worked. That probably didn't work. Major. Where's the data frame? Did you find that? It's in status, right? So should that be names? Or should that be status? Go ahead. Hit status, save it, and then knit it again. See if that works. Oh, can't open. Okay. Yes. Why is that? Yes. It's on the OneDrive, right? That's what says it went here and it couldn't find it. It's basically what it did. People connection calls. So it did OneDrive, university. And is that it? Or no, it's in here. Intro. Data. Oh, yeah. Okay. All right. Other errors with knitting. Might not be the only one, but again. Mistakes if it says, execution halted because something's not found. Make sure your data file actually has that read.csv line. All right. Right. So central tendency. So we're doing our descriptive stats at this point. All right. So we said when we report data, we're going to report some measure of central tendency, some measure of dispersion. So finishing up central tendency. All right. Usually we're going to present the mean. It's going to be the preferred method. Mean usually has the smaller standard error associated with it. It's it's easier to work with mathematically, tends to have a normal distribution, even if the underlying data is not. So to kind of get to that point, what we're saying is if we have, again, I'm going to use this cricket, right? The cricket leg, all right, if we measure the cricket legs, they could be skewed, all right? But if we take repeated samples and save the mean, the samples, the collection of all of those means, take on a normal distribution. So, and that's actually pretty good. It makes it easy to work with. The downside of the mean is that it's affected by outliers and also the shape of the frequency distribution. So if we're skewed one way, our mean is going to be affected by it. It's going to be affected by those extreme values. If we have 2 peaks in our data set, our mean is not going to adequately represent that type of pattern. All right. So if we have, I'm going to suggest, if we have outliers, if we have skewness, then our second choice would probably be the median. It's not going to be as affected by the outliers because it's a 50% point. All right. It's not going to be as affected by the shape of the frequency distribution. Exception again is 2 or 3 peaks in our data set. That's going to be our preference. Mean first, and then the median would be our second choice. If we have a normal distribution, it's actually a pretty nice thing to have because the mean, the median, and the mode will be the same. We'll have 1 peak, that's our mode, all right? And that top of that peak would represent the mean, and that represents our 50% point because we're symmetric around that. And we'll talk about normal distributions. We can't use this fact, though, to determine if the distribution is normal. All right? So if it's normal, these are true. If these are true, we may or may not be normal. Just one of those funny things. If we have skewed distributions, then we have this different pattern. So with our skew, we could be skewed right or skewed left. All right? This is a skewed right distribution. All right, make sure you see it. There we go. That's a skewed right distribution. It's skewed right because you have an excessive number of points on the right side of that table. All right? The way I think about it, skewed right, our distribution leans to the left. All right? If it's skewed right, it's leans to the left. Our relationship between the mean, median, and mode is that our mean will be someplace up here. Our median will be someplace right here. And then our mode is right at the peak. It's our most common value. All right, so we have a normal bell-shaped distribution. Our mean, our median, and mode are going to be the same. But as we start to skew right, these larger values pull the mean up. The mean is most affected by these large values. Then the median would be our next, and then our mode is our peak. So if that's skewed right, then we also have skewed left. All right, so we have an excessive number of points, larger points, on the left side of that table. I remember it as saying skewed left. If we're skewed left, then we're leaning to the right. Just how I remember it. With this excessive number of points, it's going to bring our mean to be the smallest value. Our median would be next, and then our mode is at the peak. So if you know that we are normally distributed, and I say the mean is 3. What's the median? Well, if you know you're normally distributed, then the median is going to match the mean. If, however, I say we are working with the skewed right distribution, so skewed right leaning left, and I say the mean is 3, what's the value of median? Median's going to be smaller than 3. Questions on that? Just general relationships. All right, So before we get to dispersion, we're going to talk about the sample statistics and population parameters. So as he said, we do samples. We take samples because we want and we want them to be representative of our population. The whole goal is that our sample statistics will reflect or will be used to approximate our population parameters. Now, as long as we have a representative sample or a random sample, then this will apply. But it doesn't apply for all of our statistics and parameters, right? What we want is to utilize these estimators, these statistics. We want them to be unbiased, meaning that if we calculate our sample mean, then that is an accurate representation of our population. All right. If, however, we calculate our sample mean and it always deviates in one direction, say it's always smaller, then that estimator is biased. And we try to avoid those. However, in a lot of cases, we can't avoid it. And what we do is then add some sort of correction factor to try to avoid having a strongly biased estimate. I present this for completion because what we use in the class will be unbiased. Sample, mean, and variance, they're all unbiased. The one that is biased is standard deviation. Standard deviation tends to be smaller than the true standard deviation. Standard deviation is used in our standard error estimate, so our standard errors are going to be smaller than what it should be. However, as you start increasing your sample sizes, the bias becomes less and less and less. So if you have a sample size of, let's say, 50, you can, or maybe even a sample size of 10 or 15, you can usually ignore that bias and make the assumption that whenever we calculate our sample standard deviation S, that's going to approximate our population standard deviation. All right? So knowing that, we're going to get to our measures of dispersion. And with our measures of dispersion, we're going to start with just the basic descriptors of the spread. So for those, we'd have two things. We've got our range and the interquartile ranges to talk about. So the range is just smallest and the largest values. It says our measurements range from here, our smallest, to here, our largest. All right. Depends on who you ask. It depends on who you ask, but I don't care how you report it. If you want to report it as the smallest and largest value, you can. So you can say 3, 10. Smallest value is 3, largest value is 10. That's fine. If you want to report it as the actual difference, 10 minus 3 equals 7, then that will also apply. All right, and the reason is because when you do range in R, it will report the minimum and maximum values, right? Where X is our value. If, however, you look up online or in a textbook, the range may actually be represented as how many units are spread between the smallest and largest value. Well, that's the difference. If you wanted to get that, then you would calculate the range and use the diff function to take the difference between those two values. Trying to think. I think my daughter in elementary school, when they did the range, they reported the difference between the minimum and maximum values. I think that's how they were being taught. To me, that's a little uninformative, because if we're interested in the range, we're really asking what's the smallest and the largest values, right? So this just gives us a general descriptor of dispersion. It tells us minimum and maximum value. It doesn't really tell us how many of those values are at the minimum or the maximum value. So you can have one value at 3, one value at 10, and then you can have all of the other values between 4 and 6, right? So the range is 3 to 10, but almost all of our data are concentrated right around 5. So because of that, we generally don't utilize range as much. You can if you're doing like morphometrics or species description, but usually we don't typically report it. Interquartile range, on the other hand, is different. interquartile range gives us the first and the third quartiles. All right, and it is in R, IQR is the function to give us that interquartile range, and IQR will give us a difference between those two values. This actually represents a pretty good measure of dispersion because now it's taking the 25% and the 75% point. So it's basically telling us between this range, we have 50% of our values. All right? And these are the central 50% of the values. That's actually pretty good. It's not going to be affected by outliers because those extreme outliers are going to be excluded from that 50%. So it doesn't matter if our 10 value is actually 20 or 30. We're still getting the same 50% point or 50% bulk distribution. All right. The range, interquartile range. If we work with medians, then we typically report our interquartile ranges with that. Now, what about dispersion? So both of those kind of give us ranges of our values, or we get bulk 50% points. Interquartile range does give us a better idea of where do most of our points fall and how closely do they fall together. But we don't report interquartile ranges when working with means. For that, if we're going to report a mean, then we have to have some other measure to report dispersion. All right, and the measure that we're going to get to will be our standard deviation and our standard errors. All right, but to get there, we have to understand how these standard deviations are calculated. So standard deviation is essentially an average of the deviance. All right, an average of a deviant. Well, what's a deviant? A deviant is the difference between each value and the population. All right, so draw a graph here. All right, so we have, I'm going to say 5 data points. All right, so we have 5 data points, and I've spread them out. All right, I spread them out, and we have this is our sample average. All right, so the average of all of our points central. All right, our deviant is that difference, the difference between each point and the mean. All right, now that could be a measure of dispersion, because it gives us an idea of how much variation we have around that mean. However, when we take the sum of all of these, they add up to 0. They add up to 0. So if I just stack these on top of each other, the lengths of these positive lines are going to match the lengths of our negative lines. All right. So because of that, then people would take this difference and square it. All right. When you square each of those deviants and add it up, it becomes a convenient term called the sum of squares. All right. So now we're starting to get a better measure of dispersion. The larger this value, the more dispersion you have around that line. All right. But this sum of squares is going to be affected by our sample size. Because as we add points, we're going to keep adding on an additional square deviant. So it just keeps getting larger and larger and larger and larger, which we want to avoid. What is that? Yeah, but the elevator's down at the other end. Man. All right, so if these sum of the squared deviates just keeps getting bigger and bigger and bigger, what if we standardize or normalize that value to our sample size? So now, it doesn't matter how many points we add, we're going to divide it to essentially come up with like an average of these square deviant terms. All right? When we do that, that is actually called the variance. All right? So that is our, this here is our variance difference value, or so the difference of each value from the mean squared, you add them all up, and then you divide it by the population. Now, or the sample size. Now, here's where it might get a little tricky. All right, for our population, we know every single value. All right, so when we calculate the population level variance, we divide by the sample size, and we'll get this population variance term, sigma squared. With the sample, however, we don't know everything. We don't know what our true value is. All right, we don't know what our true population mean is, in essence here. Yeah, we calculated for the sample, but we don't know our population. So if we just divided by n, we would get a biased estimate. Our value would be too small, too small. So somebody went through and said, well, if we just subtract 1 from our sample size, we remove almost all of that bias. So when we take our sample, sum of squared deviates, and divide by our sample size minus 1, we also get a variance. But this is our sample variance, s squared. And this effectively becomes an unbiased estimate. There is still a little bias, but it's effectively unbiased. All right. The other mathematical explanation is that the reason we subtract the 1 isn't necessarily for the bias nature, but it's for the fact that we estimated our mu, our true population mean, by using the sample standard deviation. And once we did that, then we lose a single degree of freedom, hence the n minus 1. So when we talk about degrees of freedoms for the test, and we have n minus 1, or group 1 plus group 2 minus 2, this is what we're talking about. All right, so the problem with variance is that our units are units squared. So if we measure this cricket's leg, all right, the leg average is going to be in millimeters. The variance is in millimeters squared. How do you rationalize? Because squared millimeters is more of a surface area, right? So what we can do is take our variance as s squared and do the standard deviation, or do the square root of it. And this gives us our root mean square, the root mean squared deviation, or root mean sum of squares. RMS is how you'll see it. This is our standard deviation, the square root of the variance. Now what we've done is taken our units that used to be in squared terms and made them the same units as our mean. Could we do this by hand? Yes, we can. I present these two equations. So this one's actually a little bit harder to use because you have to go data point by data point and have to subtract the mean and then square it, and then do the next one and square it, next one and square it. If you had to do it by hand, I actually recommend this formula, which is just this formula expanded, the expanded form. So you can take each value, square them, and then add them up, and then you subtract sample size times the square of our mean divided by n minus 1, that gets the variance. You could do it by hand. Or you can take your data set, enter it into the calculator as a data vector. And then the calculator on mine, once I get it into statistical mode, I can calculate my sum of the x squares. So I can calculate this in my calculator. I can calculate the sample size in the calculator, or my calculator can give me my sample size. Calculator can actually just give me the mean, no problem. And once I'm in statistics mode, all I have to do is do shift number 1 and it reports my mean for it. The scientific calculators can do it, any graphic calculators can do it. How are we going to do it? We're going to use R. So functions for R, pretty easy. Var for variance, SD for standard deviation. All right. If we wanted to use the square root version, Square root of the variance, well, we're going to use variance, and then SQRT to get our square root of the value. But why would you use this when SD does it for us? All right. So on these functions, we have to give it a numeric vector, and if there's any missing data, we have to remove the missing data first. If you don't have missing data, then you can ignore the na.rn. All right, so here's two data sets. All right. So as practice, I have it on here calculated by hand. We're not going to calculate it by hand. We're going to use the computer. We're going to use R to calculate it for us. So you can get these two vectors into R. You can give them whatever name you want. And then for this first vector, I ask you to calculate the variance and the standard deviation. For the second vector, I ask you to calculate the range and the interquartile. You get it? Yes? Hopefully. Don't worry. I guess I did type it fast. Get playing that on the old computer games. Have to use a keyboard. It wasn't point and click. You actually have to tell your character, look under a rock. Take gold. And you couldn't pause it either. You had to type quickly. If you paused it, it wouldn't take keyboard. Had to learn how to type quickly. Did you get them? Oh, those are off. Well, 14 and 23, okay. Ooh, 4. Well, no, difference between 14 and 23 is 9. Okay, and then your interquartile range, yours was 4. So I'm 14, 17. Yeah, give us the 19. There's 219. That's a good example, though, of how the range doesn't really adequately reflect dispersion, because you had one less number, but you still had the exact same. All right, so here's mine. So it started off with dispersion. Dispersion as a measure of variability. So I just labeled it out that we're going to create our 2 vectors first. So I called mine disp1 and disp2. Just kind of, I thought dispersion 1, dispersion 2. Whatever you use works. All right, so you don't have to change it. All right, so for disp1, all right, that first vector, I said to calculate the variance of standard deviation. So it's var and SD. Those are the 2 functions, and they take our numeric vectors, which is what we have. So variance is 1.367. Standard deviation is 1.169. Now, if you didn't believe me that the standard deviation is the square root of the variance, you can always do the square root of the variance of disp1 and see that, yes, it is, standard deviation is the square root of the variance. So for disp2, I asked you to calculate the range and the interquartile range. So I did the range and I did the difference of the range, just so you can see the difference between them. If I ask for the range, you can give me 14 and 23. That works. I'll count it. If you give me 9, that'll work, because I will be able to see your actual code to know that you did it correctly. And also, we're going to be working with the same vector. For the interquartile range, I have 3.5. Is that what yours was? 3.5? All right. So the interquartile range is the difference between our first and our third quartile. So we could also just kind of double check that. So using the quantile function of disp2, the prob is 0.75, and then I could take the difference, so subtract quantile of disp2, prob is 0.25, so first and third quantile, and you can see that we get 3.5. Now, why it gives us 75%? Good question. But what matters is this 3.5. That's
prefer us to do it in one chunk like that.
Do I prefer it to do it in one chunk like that? It would. The exam question would be like part A, B, C, D, and E, and I'd have a chunk for each of them. So part A might be calculate the variance, part B might be calculate the standard deviation. So it'll be like one at a time.
That's how I did it.
Yeah.
Was curious.
Yep. No, it's kind of like with the homework, what I've been doing. All right. What's next? Okay. So frequency tables. Everything that we've learned, we can do it in the frequency tables. All right. We can do it, work it out by hand. All right. And you know, the mean is the weighted mean. The variance is basically doing our deviate and then and squaring it and then weighting that. So we could do everything by hand, all right, with the frequency tables. But what we're going to do is show you how to get this in R, all right? Because we worked through the frequency table and I showed you how we can go ahead and do the mean using the weighted.mean function, all right? But we don't have an equivalent for variance and standard deviation. So if we're going to work with frequency tables, what we're going to have to do is transform this table into a vector and then calculate our summary statistics. So let's go back over here into our R, and I'm going to make this a new heading and say transforming frequency tables. And this will be extremely important to have. So the whole idea, the whole point, why we do this, is that sometimes you are given a frequency table. And then you are asked to calculate some summary statistics. We can use the weighted dot mean function to calculate the mean, but there is no easy way. No easy way. There is not an equivalent way to calculate variance and standard deviation. In order to calculate these, we need to transform the table into a vector. To do so using the rep function. All right, so our function is rep x t. X comma t. And I'm going to introduce you on how we repeat values. All right, so this function, this will repeat x. So whatever is in x, it'll repeat x t times. For example, rep, I'm going to do a in quotation marks 5, will repeat the letter A 5 times. And we can see that. So I can do rep A comma 5. All right, and I can repeat A 5 different times. So for a frequency table, we know what our value is, what our x value is. We know how many times it appeared in our table. All right, so slide this over, because that's what this is. We have our x, like x is 0. That 0 is repeated 24 times in our table. This 1, it's repeated 56 times in our table. All right, so we're going to use the repeat function to take this frequency table and transform it back into a vector. All right? So continuing with our repeat, this function will repeat whatever x is, including vectors. All right? Including vectors. So, example. I can do rep, and I will do a vector. So I'll make a vector of m and f. All right, so we collected organisms, recorded the sex, and we recorded as M for male, F for female. So this chunk, or this function, it'll repeat that the M, F sequence 3 times. So it's going to be the sequence. And we'll see it when we run it. It goes MF, that's the first time. MF, that's the second time. MF, that's the third time. All right? So we gave it a vector. The repeat function will repeat that vector.
the function can also take vectors for the t option, or the time option. Example, we collected, say, 5 males and 10 females. This is how we can repeat M and F the appropriate number of times. So instead now of repeating the vector M and F, what we are going to do is repeat male 5 times and repeat females 10 times. So the reason why this works is R looks at this function, looks at the rep function, and says, okay, I have a vector, and the vector is 2 items. That's my first. This is what we're going to repeat. And then I look at the times option, and I also have a vector, and that vector is 2 items. What R will do then is say, okay, we're going to look at the first item in the vector, and that must mean the number of times that we're going to repeat is the first item in the times vector. So what we do, it went item by item in those vectors to repeat them the appropriate number of times. So R sees 2 vectors in the function and correctly assumes that you want to repeat the first item t times, where t is the first item in the times vector. It repeats for the second item, third item, and etc. So we can give it a vector of 10 items, 10 values. And then we can give it a vector of time, where each item in that vector is saying how many times to repeat the matching item in that first vector. All right? So using this information, using this background information here, what I want you to try to do is to take this frequency, and I'll put this back up, this frequency table here, and convert it into a vector, a single vector, where the numbers are only 0, 1, 2, 3, 4, 5, 6, 6. For Friday, or Wednesday. All right. Use the rep function, see if you can mess around with it so that your vector ends up having 24 zeros, 56 ones, 63 twos, 34 threes, 18 fours, 3 fives, and 2 sixes. All right. So try and make that vector, and if it works, then when you issue the mean and the SD command, you should get values. All right. So we'll pick this up on Friday. Cursor. We'll pick this up on Friday, and I'll show you how I do it, how I did it. All right. We'll confirm. Make sure you know how to do this, how to transform a table to a vector. And actually, if you do it correctly, when you use table and then whatever you call that new vector, you should produce the exact same frequency table. All right? All right. Stop there. And I just added here, etc., based on the position in the times vector. So we can match them up. The first item gets repeated first number of times, second, third, fourth. All right?